Hi everyone, my name is Max Brandt. I'm from Infineon, Germany, and today I want to show you a presentation of the paper I submitted. The paper is about what can we do with trace data and how can we improve debugging for modern hard real-time systems. So at first, why do we want that? So debugging is very expensive. This is a statement from 2013 stating that the average time a developer spends for debugging is about 50%, and this raised annually bill of $312 billion. So, and now consider that this is from 2013. So now we have 2020, and I guess it is even more expensive right now. So another problem is, especially in field, when information is missing, wrong, unreliable, we have many more problems because debugging gets even harder. So imagine you're in the field and there's an error appearing, but no one knows the complete system due to IP or something, then you will have a big problem. You could now start with reverse engineering, but this is of course cumbersome and maybe not the best idea. But we always can rely on the binary data that is running on the device itself and also on the trace data that we can get from the device, because it is what really is there and what is executed. So this is always, or at least it should always be, completely reliable. So the idea here is now to use this to have a fast and good understanding of the system, even though we don't have all data given beforehand. So imagine you have a black box system and something goes wrong there, and you know, okay, there is probably an RTOS, but you don't know which RTOS or which tasks are running on that RTOS, but you just want to have a clean view on the system. So then you can use the algorithm we propose here for basic analysis, which will uncover all the tasks and the RTOS itself. And the way we uncover it can also be used later for the monitoring. So then you can verify your timing constraints and see, okay, there's a task running way too long. That should not be the case, and you can start to find responsible person for this task. So general idea is that on these systems there's application code, of course, running, which are the tasks, and there's a code regarding the RTOS, which is used for the maintenance of the tasks. So in the first step, we try to identify this application code, which might be the task set, but we don't know this yet. But in the second step, we try to identify a so-called context switch descriptor within the RTOS routines that is used for the task scheduling, dispatching, and maintenance. With this, we can then verify on one hand that this is really the task set, and on the other hand, we can use it for the monitoring itself. So the algorithm is split into two main phases. The first is the probing phase. I will go into detail on each phase soon, but as an overview, the probing phase just probes the complete system to see what is going on there. So what can we expect? And from this, we derive several groups of functions that might be a task set, so one of these groups. And in the second phase, the context switch descriptor phase, we use these groups and try to identify this context switch descriptor, which then verifies that this group is really the task set and that we can use it for the monitoring. So at first, the probing phase, this is an example trace taken with the MCDS trace trio from Infineon. And here we perform a non-intrusive hardware tracing with only function calls and returns, without time information or memory access information. And from all these calls and returns, we can now reconstruct a dynamic call graph. So with within this call graph, we see which function is calling which function and which function is called by which function. And this call graph is then used to identify these groups I talked before. They are taken regarding two conditions. So one group is always built from all functions that are not directly called. They are maybe called as an ISR, so an interrupt service routine or something else. So this is in this graph, for example, F1, F2, F3. And then we have two other groups in this example that share one parent task. So for example, F5 to F7 share one task, one function, F3, and therefore we consider F5 to F7 that this is maybe the task set because they are all executed or started by one parent function. And of course, the same can be applied for F9 to F11. These groups are now used in the next phase to find a suitable CSD for each group first. So it is very important that each group is tested independently. So we only look at one group at a time and to find this CSD of one group. So how the next phase, the CSD phase, is how can we find these write accesses where we find the CSD. So this is fairly simple. We have three functions in this example for the first group, so F1, F2, and F3. And we place a trigger at the beginning of this function, which will stop our trace. And then we turn off time information because we don't really need it here. But we turn on the write accesses that we can trace and see the write accesses. And since the trace stops at the beginning of F1, we know that when the trace stops, the write accesses that appeared right before the trigger are the write accesses that should be from the RTOS. So this is done for every function. And this is done also several times. So for the first group, for example, we do it 3 times for each function. And this leads to 9 fragments in total. So one fragment is one trace with a trigger. And in these fragments, we now have only write accesses with consisting of the address and the data of the write access itself. So here we can now start to identify the CSD, or in other words, to find an address that is the CSD. And this is done by 2 assumptions. Or not 2 assumptions, more like 2 conditions. First is that the data that is written to a specific address is the same among all fragments, because we expect this data value as, for example, the task ID or something. So if F1 is executed, it should be always the same data that is written to this address. And the other condition is, of course, that the data values are not shared among these functions, because if F1 and F2 would write the same ID in front of the start, then it's obvious that this cannot really be used as a task ID or something. So in total, these are the 2 conditions. And with these 2 conditions, we check each address. And it is also important to note that if for one address, if there's no data value, so there's no write access for this address, then we just remove this function for this specific address, which leads to something we call coverage. So if we look at this example, then we have a coverage for address 3. So for A3, we have a coverage of 3 because it is found on all 3 functions. If it is missing on F3, then we have a coverage of 2 because it is only found on F1 and F2. So if we look now at one group, we have several addresses. And here in this example, A2 has a coverage of 5 because it is written in front of 5 functions and the conditions are held by every write access. So we will pick this as the CSD candidate because it has the highest coverage. And it is most likely that if this group is really a task set, that this address describes the task ID. Now think of, we have several groups which we investigated independently. So now we end up, for example, with 5 groups, and every group has the best CSD. And in this example, G3 has the best coverage. So the CSD candidate of G3 has the best coverage with 5. So we pick this as the task set. So the chance is, from our test, I will show later, at 100% that this is not a task set. And from the coverage, we can now also derive the function set are the tasks itself. So we know that F1 to F5 were in the group, and we found for these functions the CSD. Then these functions are mainly the tasks, and F1 to F5 are the task set. So this is the final result of the algorithm. We get the address, we get the functions that compose the task set, and we get the different data values that are written in front of each task. So now we can use this for the monitoring. And the monitoring is quite straightforward. So we know the address range of each task, and also what they call and return. So we can use this address to see if a task starts, continues, or ends its execution. And to lower the bandwidth of the tracing that we need, we can turn off timestamps in general and trigger only timestamps when the CSD is accessed. So in this example, at time 10 milliseconds, we see that CSD is set to 2, which is the ID in this example of tau2. And we also see from the address that tau2 just starts its execution. And then at t20 milliseconds, we see that the value of the CSD is changed to a different task, in this case task 1. And we also see, okay, task 1 now started execution, but we don't know yet what happened to task 2, because we don't know if task 2 has finished execution or if it will continue or whatever. So therefore, we have to process the complete trace, of course, and then we can see here that at t30 milliseconds, the CSD is set to 2, and task 2 continues its execution because we don't start at the start address of the task 2 here again. So this must be one instance which we are looking at task 2. And then CSD is set to 0, which might be another task, or maybe the idle loop or something else. We don't know what happened to task 1, task 2 at this moment. But now we see, okay, task 1 starts again, and we see the start address. So the part of task 1 we have seen before must be one instance of task 1. And the same happens for task 2. We now see that task 2 starts again. So the first 3 blocks from task 2, including the time from 20 to 30 milliseconds where task 2 is preempted, this is one instance. And this data can now be used to derive parameters of the tasks itself. So we can, for example, compute the execution time, the response time, the period, jitter, slack time, and so on. So this is now the final data we get from the monitoring. We have done quite a lot of tests. So we used 3 different operating systems, and we randomized 150 task sets in total, and tested the algorithm and the monitoring itself on these task sets. And it came out that every task set was identified correct, and that the observational error was below 3.5%. The observational error for the period, so the left for the execution time on the left, looks a bit confusing because Erica OS in this case is way worse than the other two systems, but we also found out why this is the case, and we discussed this in detail in the paper. And we also have done some more tests. So one test covers false positive detection. So how can we force the system to have false positive detection of a task set, and what can we do that this won't happen? So there are unfortunately cases where we can't do anything, but from our perspective, this case should be really rare, if not never happening. So we don't expect that this case ever happens. And also we tested a task set with more complex code from a benchmark suit. And also here we were able to identify and measure everything correctly. So as a summary, this is a cost-efficient way to debug and analyze hard real-time systems. It is automatic, so this algorithm itself is automatic, non-intrusive, and error resilient. In terms of configuration, so there is not really much the user can configure. So there's not much space for configuration errors, and it's easy to use for task monitoring. So thank you for listening.